Pas due.
Juste comme ça.
Voilà.
Tu vois où l'économisme
I will make two short comments. First of all, about bimodules. What corresponds in the abstract situation to bimodules? Okay, I will give you two examples. First, in the classification of commutative unipotent group by Dieudonné and myself, there is some object which is a bimodule, which is, if you take the Witt vectors, so on the one hand, it's a group scheme, so it's an element in the category G. On the other hand, it's acted by some module, by some ring, and what I describe as a Dieudonné ring, but I can give a better description. The Dieudonné ring is simply this ring of endomorphism in the category G of WP infinity. That's a short definition of this. So, of course, on VWP infinity, first of all, you belong to a certain category, and then you have an action of a certain ring. Now, what you have to prove is that this ring is generated by the FP, VP, and so on that I described, and so you have to give a presentation of this ring. But it's better to define it intrinsically this way, okay, which doesn't distract you from calculating this exact structure. Okay. So, now, on the other hand, in this case, and that was remarked to me, that when you compare, you have this functor T from the category C to the comodules over C. Then there is a certain object which is, in a sense, a bimodule, which means that it is an object, on the one hand, it's an object of C, or rather inductive limit of object of C, which is considered as a comodule in the obvious sense. You can define the comodule as an abstract category, of course. Tensor product is dissymmetric. So, and now what you have, you take this.
Is it T or lambda T here?
I'm sorry?
Is it T or lambda T?
No, right. We started with T, and we constructed the coalgebra and the functor. That's a lambda T that I want, okay. So I have this functor. Okay, now, as I said, if you want to have an object, a mixed object, which is partly in C and also a comodule, that's the one you have to consider. And I was corrected by Francis. I was a little annoyed because, no, I have only one Tx. This is an object in C. This is a finite dimensional vector space. This is a finite dimensional vector space. So the tensor product makes sense as an object of C. Now you have an infinite diagonal in the quotient, which means that it's in a suitably enlarged category of end object in the category. And now the point is that this object, if you apply T to it, you recover the coalgebra. So the coalgebra lives in the category of vector spaces, but you can lift it by T, or rather by the extension of T to in limit, to an object or in object in the category C, which all the properties. And of course, like the tensor product can be used to describe the inverse, well, in the Morita equivalence, the tensor product can be, or its inverse can be defined by a tensor product, a generalized tensor product. Similarly here, you can define the inverse functor from this to this by a certain tensor product. Okay, that's what I wanted to say. Now, second remark, I was working with one functor from C to vector space. And I got CT with a coproduct CT tensor CT. What if I have two functors? Now, suppose I have two functors, T1, T2, so from C to vector space, Fk. If I have two vectors, F C1, T1 and T2, what do I have? I can build out of that a C T1, T2, or T2, T1, maybe, T2, T1, with the following property. it's a co-module to the right with respect to CT1. That means there is a co-product which takes CT2, well, it takes CT2T1, CT2T1 into this. And there is similarly, on the left, you have CT2 tensor CT2 times T2T1. That means it's a right comodule with respect to this coalgebra and a left comodule, the bi-comodule. Furthermore, if you have three functors, T1, T2, T3, you have a co-product which brings you T1, T3, or T3, T1, T3, T1, into CT3, T2, tensor C, T2, T1. It's dual to a composition, which goes, well, CT1, T2 is in a sense the dual of the natural transformation of T1 into T2, to some extent. And so the composition of natural transformation gives you this. But playing with the explicit description I gave and with generator of this kind, it's easy to define. Okay, so that's what I wanted to say about, to supplement what I've said before. Now let's go on and apply these ideas to geometry, which, of course, all the invention of Tannakian category by Grothendieck and his associate was motivated by geometry. So first example of application. Okay, I'm taking a certain topological space, call it E. E is a topological space, and I will define a category as follows. C is a category of local systems, or rather of local, of sheaves of Q vector spaces, but I could replace Q by any field, Q vector spaces. For the application, that's what I need, Q vector spaces, which are locally isomorphic to QL, to a constant sheaf of the form QL constant. Sheaf which is constant over a small neighborhood of any given point, you can trivialize your bundle and the fiber are finite dimensional. That's the category of sheaves. Now, as functors, you suppose you take any point X in E. As functors, you associate to any sheaf F its fiber at the point X, which is a finite dimensional Q vector space. So my category was, so you will get a functor from C into the finite dimensional vector spaces over Q. Now you restrict the category to what I call C unipotent, which are the object, unipotent, are the objects which have a filtration, finite filtration, such that the quotient are trivial bundle, trivial sheaves. So locally they are locally trivial, but globally you assume that you have first, of course, a sub sheaf which is constant, globally constant, then the quotient by this another sheaf which is globally constant, etc. So it's an extension, a successive extension of globally constant sheaves. That's what I translate. Now what you have, the point is that you can, this is unipotent monodromy. It is known that if E is connected and let's say locally simply connected to one, any manifold to simplify. And if you have a manifold which is connected, if you choose a base point x0 in E, then you have a group pi 1 of the space E at x0, pi 1 of E at x0, And it is known that you have a natural action. You have a natural action, that's a monodromy of the pi1 at the point x0 to the fiber at x0. So you have a natural action acts on fx0. But pi1 of x0, suppose it's a manifold, locally manifold, it's a manifold. This group is a finitely generated group. The pi1 is finitely generated. Oh, no, not necessary. No, discrete group. Okay. If you have many holes in a plane, you have infinitely many generators in the pi1. Okay. So it acts on the pi1. But so so now you can go to the representation of over Q of some group pi1 of x0, Ex0. Okay. But this pi1 is not an algebraic group, it's a discrete group. How do you reconcile this with the previous theorem? This is as follows. By the previous theory, you have an equivalence. Well, of course, there are natural tensor products in this category of locally constant sheaves. Therefore, the dual, what you have, the coalgebra as it's a Hopf algebra. It's a commutative Hopf algebra. So the spectrum of this commutative ring is an algebraic group scheme, a affine group scheme. So what you have is that you have here, so associated to this general situation, my algebra or coalgebra or bialgebras correspond to groups. And indeed, in this situation, what you have, when you have two such functors, you have a certain algebraic space, algebraic manifold or scheme, which is acted on one end by some group, and at the other end by some group. It has two group actions. And the composition can be understood in this way. And the point is that if you take this with this action, it's a principal homogeneous space or a torso, which means that if you consider the space corresponding to this coalgebra and the multiplication, then it's an action of the group. The group is a simply transitive action, which means that given 2 points in the space, there is a unique transformation of the group which brings x to y.
Sorry, who is T1 and T2 here?
Well, I come to that. Okay, T1 and T2 are just obtained by taking 2 base points. So that's what we have now. Okay, what we have is that if you take 2 base points, x0 and x1, you have 3 objects. You have the loops around x0, you have the loops around x1, and you have the path from x0 to x1, up to homotopy. So, of course, and if you have a third point, you have this, and a composition, which reflects this abstract form of this composition. So what you have is that here you have the set of all paths from x0 to x1 up to homotopy. They are acted on the right by the loops at x0, on the left by the loops at x1. But given 2 maps from two paths from x0 to x1, there is a unique action of some loops at x0 or unique action of some loop at x1, which brings them together. It's a groupoid. So if you want the collection of all these paths from x0 to x1, they form a groupoid, and if you fix a base point, the groupoid reduces to a group. And we could formulate things abstractly, introducing abstract groupoid, it should be the same. Okay, so now the point is that the paths from x0 to x1, or the loops around x0, they don't form an algebraic variety. But if you restrict, if you apply my general construction to this category and to this functor, or these functors, you will get something algebraic. Which means that, well, I will use pi of E and BA for the homotopy classes of paths from A to B. Homotopy classes of paths from A to B. A, B, homotopy classes, up to deformation. Okay. I don't put 1, but this is, of course, it was not already in the 30s by the German topologists that the fundamental group has to be replaced for a space by a groupoid. You don't take only the loops at one point, but you pass from any point to any other point. I don't remember who did that. And it was forgotten after that. Is that? Brandt. No. Brandt was motivated not by topology, by user. No, well, I forgot. One of the, maybe, okay, doesn't matter. Okay, so now you have this. But what we want is to replace this by a collection of algebraic groups and spaces which are operated on the one side and on the other side by algebraic groups. Now, the general procedure that you have is as follows, and basically due to Quillen and to some extent to Serre, but it's formulated explicitly by Quillen. So take gamma, which is this group, fundamental group at the point x0. Now take the group algebra of gamma, finite linear combination of elements of gamma with rational coefficients. In that, you have the augmentation ideal. That means the subvector space which admit as basis the gamma minus 1. Gamma runs over the group, different from 1 and minus 1. So this is the basis, the gamma minus 1 from a basis of I. It's an ideal, so you can take the square of this ideal, a two-sided ideal, etc., etc., etc. You have a decreasing filtration by powers of the maximal of the augmentation ideal. By duality, what is the dual of the group algebra? Is a set of functions from Q to gamma, from gamma to Q. Sorry. The element of gamma being a basis, I mean, a linear form is defined by its value on the basis, Q gamma. Now, if you have this decreasing filtration, by duality you get an increasing filtration. There. So you get, let's say, call it A0, A1, A2, etc. Which are part of the dual. So A0 is the orthogonal to I, A1 is orthogonal to I squared, etc. Since we have, when you factor Q gamma by a power of I, it's an algebra. By duality, these are co-algebras. So there's an increasing sequence of co-algebras. And now you have an increasing sequence of co-algebra. Now the multiplication in the function, the multiplication of the functions. Well, you have, in Q gamma, you have a co-product whose dual is the multiplication of functions, pointwise multiplication of functions. You have a product in Q gamma, which is extend the multiplication of group gamma, which by duality define you a co-product. So, and this co-product, so you have an increasing sequence of co-algebras. But now the multiplication, of course, the multiplication takes you AP times AQ into AP plus Q. That's easy, or maybe Q plus 1. AP to AP plus Q. Which means that the union is an algebra. Not every single AP. The union is an algebra, and it's a filtered algebra in the standard sense. So the co-product will take A as a limit, UP, AP. So there is a co-product, A into A tensor A, which brings each AP into AP tensor AP, bringing AP into AP tensor AP. And there is a multiplication which satisfies. In the limit, you get a Hopf algebra. And this Hopf algebra is commutative, because the multiplication is a pointwise multiplication of functions. It's commutative, but not co-commutative unless the group gamma is commutative. So, why do you have a Hopf algebra? And now again, taking the spectrum of this algebra A gives you an algebraic group. Well, infinite dimensional and general algebraic group. So that's what the way you can associate to any abstract group. You can take any discrete group, perform this construction, which is due basically to Quillen, and you get what I will call gamma unipotent n, which is a spectrum as a scheme, it's a spectrum of this algebra A, and the multiplication being defined as a coproduct in A, and this will be a unipotent pro-algebraic group. It's easy to show. And therefore, what you have is that gamma maps into the rational point of gamma unipotent. So you have an algebraic group which is defined over the rational. It makes sense to speak of the rational point, and then you have this map. This map is not necessarily injective. If I start from a simple group, for instance, the corresponding gamma un will be trivial. So you may lose some information. But what it is that if I do this construction, it's exactly my general construction applied to the category of sheaves of Q vector space, which are locally isomorphic and which are unipotent in the sense I explained. There is you can start with a global trivial sheaf, then you extend it by another one, by another one, by another one, by another, by successive extension of trivial, globally trivial sheaves of Q vector spaces. And so what you have is that it is known by topology, that the locally constant sheaf correspond to representation of pi 1 without any restriction. And now, if you look at my subcategory, which would correspond to unipotent representation of the pi 1, that means pi 1 mapping into some triangular group, then if I apply my general theory, I get another equivalence of the category of these sheaves with the representation of some unipotent, pro-unipotent group scheme. And the translation is that gamma, as a discrete group, is maps into the rational point of gamma unit. And this is gamma unipotent is a unipotent completion. And that's what we will use. Now, of course, if you have two base points, as I said, if you have two base points, any map, if you select a certain map from x0 to x1, any other map is in a unique way the product of this unique map, this unique path with a loop there. And therefore, you can transfer everything, which means that if you have two base points A and B, you have, so here you have, now you have pi 1, you have pi 1 of E at 2 points, B and A, and you have the unipotent completion. So this is inverse limit, so it's a scheme which is a affine scheme, inverse limit of finite dimensional scheme, which is operated on the right by the pi 1 unipotent of E at A, and on the left by something similar for B. And that's what we need. Okay. That's the first application of our general theorem. And which was, well, it's a combination of the ideas of Grothendieck about what is monodromy and the work of Quillen. As you see, the advantage of the work of Quillen is the following. If you have an algebraic group, it has a Lie algebra. And therefore, if you associate to any abstract group an algebraic group, you generate a Lie algebra over the rational. And this Lie algebra is quite important. And for instance, if you apply this to the braid groups, you get, well, if you consider the pure, let's say, consider the pure braid groups, then the corresponding, you do this construction, you get an algebraic group scheme, and you get a Lie algebra. which is exactly what we need in the application to monodromy, etc. Okay, so that's the first thing. Now, the second thing is the following. I will consider a certain category, and I will consider two factors and the comparison between the two factors, but it will be not over one given space, but it will be universal over a certain category of space. That's now the strategy of motives. In one sentence, what Grothendieck had in mind when he invented motives is that if you have an algebraic variety, you can define a number of cohomology theory associated to an algebraic variety. I will give more details in a moment. Well, ordinary cohomology, which is what he calls Betti cohomology, the Ram cohomology, were familiar in differential geometry and topology. He invented the L-adic cohomology, he invented the crystalline cohomology, invented many other cohomologies. The point is as follows, that to a given algebraic variety, you can associate a collection of cohomologies in various theories. What you expect, for instance, is that whatever the cohomology theory is that you choose, the dimension, the Betti number, the dimension of the cohomology group will be the same, which is not yet completely settled at the moment. The L-adic cohomology for the various prime L, we don't know yet in full generality that the Betti numbers calculated as a dimension of the QL cohomology is the same independently of L. That's still an open problem. So Grothendieck said, I have too many cohomology theories. There should be something behind it. And what he had in mind was like a lighthouse on the seashore, turning during the night, and sometimes you see this small village, this church, this wood, etc., and around. So he had the idea that there was a central lighthouse which would shed light, that's his image. It would shed light, and what you see, the various cohomology theory, and they would put light on the various cohomology theory and be what is really behind all this cohomology theory, what is the motive. And motive, he said that motive is because it motivates you, and on the other hand, it's borrowed from music, musical motive. Okay. So, and then Grothendieck had in mind that there should exist universal cohomology theory, which he calls motivic, and that there should be, given any space, any algebraic variety, reasonable algebraic variety, you should associate to it certain motivic cohomology group, and then in a certain category, which should be a Tannakian category, which will correspond to the representation of some group, as we have seen, and then you would have functors from this motivic cohomology to the other cohomology. It seems that at the moment, after Vojevodsky, this category of motifs is partially defined. Okay, I will not insist on that, and at least for the cases we use in motif for multi-zeta, it works. So, and this theory exists to some extent, and Deligne, who is rather conservative in this respect, say, well, I don't know if it exists, but at least I know the incarnations, I know the, what he calls that, the realizations. So, I've different cohomology, de Ram, Betti, etc., I can compare them. That's all I need. Well, we will be more modest, we will consider only two cohomology theory, which is what we need here. So, the two cohomology theory will be as follows. So, I start with X, which is a smooth, quasi-projective manifold defined over the rational. You could do with a number field, but there is a well-known construction by André Weil, descent of the ground field, which enable you to reduce everything to the rational. Okay, so quasi-projective means that it is obtained as a projective algebraic subvariety from a projective space where you remove some subalgebraic variety. An Zariski open set into an algebraic variety, quasi-projective. We want to allow not only projective variety but also affine varieties which are obtained by removing the points at infinity. Okay. Then, to this, we can consider the complex point. Well, for any algebra over Q, you have the point x of x or in this algebra, x point. They form, in the sense of ordinary differential geometry, a manifold, a complex manifold, and therefore you can define HIXC with rational coefficient, cohomology, and that's what Grothendieck and Denis call the Betti cohomology of X. And implicitly, you have always a rational coefficient. At the moment, we would be happy to do with integral coefficient, but it's too much. It's too much for the moment. On the other hand, you have so that's a vector space over the rational. Now you know by the Ram theorem that you can calculate the cohomology with complex coefficients. Cohomology with complex coefficients can be calculated via the Ram theorem using differential forms. But these differential forms are of the following type. They are smooth, they are differential form for the real manifold underlying. That means they are depends on coordinates z and z bar. Z and z bar. And they are smooth. They are smooth functions, C infinity function. That's too much to calculate this. Too much to calculate this. And what Grothendieck wanted, we wanted to write it as what he called HDX, the de Ram cohomology, or the proofreading argument, when you say cohomology de Ram, should you put the second one capital? I had a long discussion with someone at the National Library. I sent a paper and he was correcting my sheet. Okay. Let's say. So, tensor C over Q. And similarly, of course, okay. You can, in order to calculate the cohomology complex coefficient, you have two options. Start with the ordinary cohomology with coercion coefficient, and then take the tensor product. So it's HIB X tensor QC. Or, and this is it depends simply on general topology or general homology theory. It doesn't depend on the fact that you have a projective algebraic variety, quasi-projective algebraic, of course, I would say algebraic manifold. What is special in this case is that here the cohomology calculated in the Ram form can also be taken as something over the rational extended. And they should be isomorphic. Now, how did Grothendieck define this? Well, I will give a simple minded definition. First of all, when X is affine, take omega or take omega R X over Q be the differential form of the type dx1 dxr multiplied by f of x1 xr, where f is some of such thing. F is a rational function. So you multiply dx1 dxr local coordinate by f of x1 xr, and you take linear sum of that. Okay. So differential form which can be expressed in the sense of algebraic geometry and rational function. This function having rational coefficient. This can be expressed as rational function, numerator and denominator being polynomial this coefficient in Q. Okay. And then you have a certain complex. You have certain complex goes into omega r plus 1. You just take the cohomology. That's very simple. But the fact that it calculates the right cohomology is a deep statement which depends on the theory A and B of Cartan and Serre, on the Gaga theorem of Serre, etc. It depends on very strong and deep results connecting a complex variable with algebraic geometry. With algebraic geometry. So, now if x is not affine, you represent x as the union u1, us, where each ui is an affine variety, and then you have a double complex, which I call the Čech-Durham complex, which is obtained as follows. You take the various intersection ui, which is ui1 intersection uip, and you take the differential form. You take the differential form of degree r over ui, and you take the direct sum over all I being q. P. I is P is the corresponding I. That means the number of elements in I is P plus 1. You take this direct sum. Now, this is a double complex. There are 2 degrees, the combinatorial degree P and the differential degree R. And there are 2 differentials. Exterior differential acting on differential form and Czech co-boundary acting on the simplices. There is a simplicial theory and a differential theory. You have a double complex, and you take the cohomology of the total complex associated to this double complex. Grothendieck phrases is in terms of hypercohomology of sheaves, etc., or resolution of sheaves. This is a simple-minded version, which works in practice. And by the way, it was introduced by André Weil in a different setting already in 1947 in the proof that André Weil gave of the Durham theorem, and which was included in a letter to Henri Cartan, which is published twice now, first in the collected paper of André Weil, and then in a recently published book, Correspondence between Cartan and Weil, which is a fantastic book. I commend it. So that's it. So we have one way. Now the point is that if you take all your differential form built out of rational coefficients, the cohomology that you get is a vector space over the rational. But the point now is that when you extend it to the complex, so when you extend it into the complex, well, it's easy to show that you just replace the rational coefficient by complex coefficient there. But what is deep is that with this very restricted differential form, you calculate the same cohomology as with all the differential form. Okay. So now that's the point. So to any smooth projective algebraic variety, quasi-projective algebraic variety, defined by rational, we associate 2 cohomology with coefficient in the rational number and a comparison theorem of the complexified with the complexified. That's exactly what we need. Okay, now I don't have much time. The analogy is with, the analogy with 2 base points is that when we wanted to calculate the monodromy of a space of a bundle over a space of a sheaf or bundle over a space, you could compare what happened to 2 different base points. You can loop around one, loop around the other one, go from one to the other one. Here it's very similar. Compare this as 1 base point, this as 1 base point. So you can loop around, you can loop around, and you can loop around, and compare it. So what you have There are other cohomology theory, as I said, LIG cohomology, etc., but at the moment I ignore them. Okay, so now yes. Now I have to open the black box. That means, according to Vojevodsky, we know that there is a certain category, which is a linear category, which is mixed state motives. Okay, this category has a property that well, it's a certain category. There are two kinds of properties. First of all, there are realization factor, which I call HIB and HI the RAM, to the vector spaces over Q. Finite dimensional vector spaces over Q. So this category C is an additive category, because if you have two manifolds, you can put them side by side, making a disjoint union. There is a natural tensor product corresponding to the Cartesian product of the variety. Cunet's theorem explained to you that if you have a product of two varieties, the cohomology is a tensor product of the cohomology. So that's why the product, topological product, Cartesian product corresponds to tensor product in this category. And furthermore, this category, this functor exists, they have suitable properties. Furthermore, if X is what I call a Tate variety, what is a Tate variety? It's a variety which has the following property. X0, X1, X2, XD, which is X. Xi is a closed subvariety of dimension I. And if you take the difference xi minus xi minus 1, it's a disjoint union of copies of the affine space of dimension I. Alpha. It's a disjoint union of copies of the affine space, pure affine space in the same dimension. Take, let's say, the projective space. The flag is one point, one line through the point, one plane through the line, etc. And the difference between two is an affine space. Grassmannian and so on. Okay. And so, if you want to calculate, if you have something over a finite field, if you want to calculate the number of points, it's very easy. The number of points is obtained by taking the number of points of x0. The difference, the number of points of the difference x1 minus x0 is 2, etc. And each time is a polynomial in Q. Q being the number of elements in the field. So, the number of points over a field with Q elements can be expressed as a polynomial in Q. And that's well known for the projective space, for the Grassmannian, and so on. Okay. Now, that's a Tate variety. And it can be shown that when you have a Tate variety, and many other interesting varieties are Tate varieties, when you have such a variety, you can associate to it, and to each I, you can define HI motivic of X, which is an object into MT M of Q. Okay, that's the deep work of Vojevodsky. But the point is that in practice it's very easy to use. You just know a few basic properties, and to do the manipulation calculation is very easy. To show that it exists in general, I'm not able to understand how it is done. Okay, now there remain two things to be done. First of all, if I take P, the projective line P1, and I remove 0, 1, and infinity, the sphere minus 3 points, the famous title of a famous paper by Jolene. Or if you want, the finite plane minus 0 and 1, which is the same. Now, I would like to consider the homotopy around 0, the homotopy around 1, and the path from 0 to 1. But the point is, the small difficulties as follows, is that I want to consider the space X where 0, 1, and infinity have been removed. And I'm looking for paths going from one point outside to one point outside. Well, the strategy has been well understood, and Jolene has introduced the so-called tangential base point for that purpose. It's very easy to explain. Draw a certain small tail to 0 and a small tail to 1. The tail at 0 goes in the positive direction, tail at 1 goes in the negative direction. Now, the point is that these two tails are contractible points, contractible sets, of course, contractible sets. Now, it's easy exercise in topology that instead of having the path going from one point A to one point B, you can replace A and B by small pieces which are contractible. If you want to go from A to B, you can put here something, there something, and consider the path which go from there to there, from the small part for the small tail to the small tail, and the homotopy being with possibility of moving the endpoints, provided they stay in the given region. Well, since this is simply connected, it does no harm. So you can define, as relative homotopy group, you can define the path and the homotopy classes of paths between 2 points which are outside your space in this sense. And that's what you do. So now we would like to consider paths going from 0 to 1. Similarly, for the loops, they start from there, they can go anywhere, but they end up in the same small tail. Okay, this is not difficult to consider. So now what we have is the following. We have pi 1 of x at the point, I call it O plus, because it's plus here, and 1 minus. You have pi 1 of x at 1 minus, and you have pi of x points going from 0 plus to 1 minus. This is a group, and the group operates on both sides of this. Now, what we have seen is that we can have to such a consider this as a discrete group, and we were able to do pi 1 x O plus unipotent. A certain algebraic group, unipotent algebraic group or pro-algebraic group, which received pi 1 as a subgroup. Well, and now the map is 1 to 1. So you can embed this in the rational point of some algebraic group. Similarly, here and here. So the natural action, all these extend to action of algebraic group and spaces containing the topological thing, and that's what we have done. Now, you could do that also. You could do that at the level. So what we have is that we have unipotent version of the various pi 1, and the Jolene calls them pi 1 b, or pi 1 of x with a base point A, B, Betty, or pi 1 Betty. It's an algebraic group which contains the ordinary pi 1 as a discrete subgroup. Okay, now you can do the same with de Rham cohomology. Well, de Rham cohomology comes with integrating. Well, what is important is to integrate differential forms. And now I will not, well, it will be a full course about iterated integral. I have no time to get to detail it to you, integrating, but the point is that the monodromy, there is a well-known formula to express if you have a differential equation, integrable differential equation, and you consider so you have a bundle with integrable connection. Then you have correspondingly the locally flat sections. They form a certain sheaf, and this sheaf is exactly the type of sheaf I've considered before. So this is and then what you have, so these sheaves, but then if you want to calculate the monodromy, from one point to the other one, there's a well-known formula called by physicists Dyson exponential formula, and which is a way to express to calculate the monodromy by a power series which term is an iterated integral. Again, it will take too long to explain today. So, okay, what we have is that we have a certain integration process which correspond to the embeddings. So what you have is that now you have a pi 1 de Rham of x to A, which is another algebraic group or pro-algebraic group, and in such a way that the ordinary pi 1 xa embeds here more or less by this construction of Quillen, and embeds there by iterated integral. You solve explicit differential equation, and the solution of this differential equation can be formulated by some series of iterated integrals.
And to define the map on the left, you need a connection. That's what.
Yes. So, I mean, this is, well, for this you need connections that with some differential equation. But the point is that when you have pi 1 minus 3 point, there is a natural differential equation. I could explain it to another occasion. So there are a natural differential equation, and then in such a way that the coefficient of the monodromy are exactly the iterated integral defining the multi-zeta. That's the point. So what we have, the strategy is basically as follows. You have the pi 1. You have two algebraic group, pi 1b and pi 1 de Rham, which both algebraic group defined over Q, and you have a map from the topological pi 1 in both of these. That's part of the picture. Now the last part of the picture is that you have these two functors, de Rham and Betty, and at the level of cohomology, you have a comparison. Well, you could go from cohomology to homology by duality, so you have a comparison, and you know that there is a connection between pi 1 and H1, of course. The first homology group is the pi 1 made abelian. So what you expect is that you could have, so the comparison dualized to get a comparison between the two versions of H1 should be the beginning of something acting at this level, pi 1 and pi 1. So really what you have here is that here I had one base point, but really we have two base points, B and A. And B is this point, A is this point. B is here, A is here. So you have comparison to base point. You have two base points, A and B, and you have two cohomology theory, de Rham and Betty. So you have a square. And the situation is very similar, but don't confuse it. Now to finish, I will do the following. Let's see. Well, one more step is that pi 1, of course, if I take pi 1 Durham, for instance, and if I take this is a certain pi 1 of Ex at A, point A, let's see. That's an algebraic group, and I've taken the function of this. By equivalence construction, I've seen that there is a natural filtration. So I can take O sub n, natural filtration. So it's obtained by increasing n for large. Now, what can be shown is that, that's done by Delin and Goncharov, this is the same as Hn of Xn mod a certain Bn. So the relative cohomology of Xn, X is this curve minus 3 points, projective line minus 3 points, Hn of Xn mod Bn. And what is Bn? Bn is a set of elements x1, xn, with a property that x1 is A, or x1 is x2, or x2 is x3, or etc. xn is B. That means you have been removing a certain number of subvarieties, divisors. And I will finish by making a picture. Okay, so that's what we have, Bn, xn mod Bn. And that's done in the paper by Delin and Goncharov in the analytical normal. So this gives you, this is the RAM homology.
What do you mean by mod Bn?
Well, relative cohomology.
Okay.
Relative cohomology. Or I will not enter into that, but relative, there are various variations about relative cohomology, but they will give the same result. Okay, mod Bn. So what you have is that it's important that you have Hn. Now here, what you can do is that you can do the same construction. Well, if you have this space, it has various cohomology. It has a Durham cohomology. It has a Čech cohomology. Therefore, if I apply the Czech, the Betti cohomology, if I apply the Durham cohomology, I get this, starting from this collection of spaces. First, I start the Betti cohomology, apply with this, and the result is that if I take the for each n, the nth cohomology of x power n modulo Bn, you have to introduce relative cohomology, is a motif in the sense I've given before. It's a motif. That means these are cohomology groups coming from, so here you have two spaces, and they come from the same object there. That's one important thing. So, it relies on interpreting iterated integral. The fact that you have n means that you have an n-fold iterated integral. Okay, so now to finish what I have this comparison. And which means that the topological path maps in two ways from there to there. And then there is, since it comes from motif, I have a comparison map of the complexified group. Map of the complexified group. Now, what we have is that in one word, associator of Drinfeld can be interpreted in this way. Voilà. This diagram enables you to define, to give a new definition of the Drinfeld associator. As a comparison, it's a comparison, and then you should take as base point these two base points. So you have this, and now what you have is that there is, since this is motivic, you have a group which acts here, because, as I said, this functor, each of these functors correspond to a certain algebraic group. This functor, according to the general philosophy of Tannakian category, factors through the representation of a certain algebraic group, which is different there and there. And so, to finish, what you have is that you have two motivic, well, M, let's say M Durham and MB, which are certain algebraic group in such a way that the Betti cohomology maps these motifs into representation of this group, and the same for Durham. Now you have this, and then what you have is that you have P Durham B, which is the comparison between these two. As I said, the various cohomology theory can be compared. So if you compare them, what you have is that you have naturally, and all my initial construction about comodules and coalgebra in categories were too motivated by that, you can construct not only two groups, which are called the motivic Galois group by Grothendieck and his followers, by a space which is acted on both sides. And the comparison corresponds to a certain point, gamma into P dr B complex points. So all these are algebraic varieties over the rational numbers. But the point is that we cannot, well, basically the points here correspond to the associator. They basically correspond to the associator. And what we have in the associator, we know one version of the associator, the Cauchy-Zamologic of Drinfeld associator, which has real coefficients, and we don't know any other. At the moment, we don't know. Ah, we have to look at that. Francis also had some proposals. Okay. So we have to see that. At the moment, well, okay, at the moment we're still working on finding other ones, I would say. What we know that they are rational points. We know that they are rational points. We know an explicit complex point, and we are looking for other points. Okay. Now, what you have is that what is the motivic period are as follows. Yes. Here we have a complex point. And then you have a suitable, well, you have two groups acting on the left and on the right, but these are general groups, I mean, acting which define for all variety at the same time. They not refer to a specific geometric situation. That's the strategy. This doesn't refer to a specific geometric situation. It's a universal program. Then, well, if you I refer you to the link for the details, it's very well explained. Then the point is that in this you have suitable subgroup, and the miracle is that if you take this complex point, and if you take their suitable subgroup, call it NDR and NB, when I say group, I mean algebraic groups over the rational. So I have the situation. I have a space on which two groups N and B and R have a complex point. Let's take the orbit of the complex point with respect to this. It's no guarantee, so it's an algebraic subvariety defined over the complex. Miracle is defined over the rational, which is the same as saying that there is a rational and there is a rational associator, more or less the same. Okay, so now we have this. So inside of this, we have a certain algebraic subvariety, which is acted on both sides by two certain algebraic groups. And a motivic period is a function on this, which is defined by using a certain integral over a certain domain d of omega, and which has a property. So I write m here to say motive, which means that there's a certain, call it QDRB, a certain subvariety, algebraic subvariety defined over the rational. And what you have is that you have to each differential form and to each domain of integration of the same dimension, you have a formal symbol of this kind, which is a function on this space. And if you evaluate the point gamma is in QC, containing QC, if you evaluate this function on the complex point, you get a complex number. And the evaluation is exactly, so the evaluation is what you expect, the ordinary integral. That means we have ordinary integrals, multi-zeta represented by ordinary integrals. What is the strategy? We would like to understand all the algebraic relation with rational coefficient between these. At the moment, no one knows. For instance, we don't know whether zeta of 5 is irrational, which is the first step, the very first step in this. Okay. So, what we do, we promote the multi-zeta as function to some space, and we use the form, at least we use m to say that they are not considered as numbers, but as function of some space. This space has a specific point, which is even a rational point, or I say a point with real coefficient or complex, doesn't matter. Here it's real matter. So we have a certain space. Your integral, you know the value of the integral at some point. You extend this value to a function to the whole space. But this time it's a rational coefficient. So it's obtained by specialization. Of course, if there is any identity which is satisfied by this function, when you specialize at a given point, you keep the same relation. But the converse is not obvious. What we know, for instance, is that all the basic relation we know for multi-zeta, double shuffle, etc., they can be promoted to that, which is not always so easy, but it can be. So that means the double shuffle relation that are very familiar here, you can promote them. But, and we can show at least we have a much better control of this algebra. The point would be to show that the map evaluation is a one-to-one map. So we have split the problem into two about the relation between a multi-zeta. Promote all these multi-zeta to formal multi-zeta or motivic multi-zeta. Calculate with them in a certain abstract algebra, but you have many tools, many algebraic tools, and what Francis did is to uncover the exact structure of this algebra. And then you have this algebra mapping over the real or complex number. Can you show that this map is injective? That's too much for the moment. But at least we have split the problem into two parts. The first part is basically solved. The second one, it's my agenda, and my agenda I prove to be proven in 2040. Well, maybe too optimistic or too pessimistic, I don't know. Okay, so just to finish and to show you a very typical example and to show where the difficulty is and why do we need this sophisticated procedure. Okay. I take zeta of 2, very simple example, which is sum, and is 1 over n squared. I represented I represent it as follows. I take a plane with two coordinates, x1, x2, and I draw these lines. So the line, first coordinate 0, first coordinate 1, second coordinate 0, second coordinate 1, and x1 is x2, which is exactly x times x minus the diagonal. Diagonal is there. And I said before, where is it stated? Yes. x1, I remove x1 is x2. So it's a typical example. The base points 0 and 1, I've put them at infinity, so the base point, the first base point is there, the second base point is there. Okay. Now zeta of 2 can be represented as a double over this domain. So the domain is 0 smaller than x1, smaller than x2, smaller than 1. That's the domain of integration. And what you integrate, let me see, it's dx1 over 1 minus x1, dx2 over x2. Half of the audience will write the inequality in this sense, the other half in the opposite way. But depending on the day, I choose one of the others. Okay. So that's an integral representation of zeta of 2. Which is easy to derive, very easy to derive, and in general, multi-zeta have similar expression. I just take this simple example. Now, there are a few shortcomings in this representation. Well, first of all, this is, well, what I call B here, the boundary. The domain of integration which is here, this is a shaded triangle, is not a cycle in the sense of is sitting in x times x. Well, we sit in x times x. That means we remove from the plane vertical line x0 and x1 and horizontal line 0 and 1. We remove these two lines. But the domain of integration is not closed. It has a boundary in this. Well, part of the boundary is there. Part of the boundary is there, so outside the domain of the x times x. But there is a boundary which is also here, and which is in the which is inside x times x, inside m times x, and so it's not closed. Well, where if you look more precisely, if you take B as part of the plane with all the line removed, it's closed. The boundary is outside what I retained. But there is a shortcoming. The domain of integration in the plane with the line removed is not a compact. It's an open. And in algebraic geometry, we are not allowed to go to the limit. If we integrate to 0 to 1 in algebraic geometry, the function has to be well defined at 0 and at 1. You cannot allow your function to be defined. So first of all, the domain of integration should be a closed thing, or compact domain. And second, the function to be integrated should be regular at every point. Okay, so here what you have. First of all, the domain of integration, if you have removed that, is not compact. The open simplex is not compact. Second, so yes, if you want to have a relative cohomology, you have first to omit from the plane the two vertical line and the oblique line. That is taken into account here. Now about the differential, you don't have poles. That means you have to omit x1 is 1, the vertical line, and the horizontal line. So altogether that makes 5 lines. Okay, now the function that you integrate remains, the function that you integrate, this one, 1 over x1, 1 over x2, remain finite along the boundary. So it looks fine. But at this point, you have something exceptional. at this point, for x1 is 1, x1 is 1, no, x1 is 1, and no, at these 2 points, at x1 is 1, you have a singularity, at x2 equals 0, you have a singularity. So you have a triangle, and the function to integrate is singular at 2 points. Well, analysts would say a point is a set of measures 0, I don't care. But we are not analysts at this point, we are algebraists. And so we have to remove that. Okay, an intermediate step, which is well known, is another integral representation, which is as good, but not yet fully good. I take this time, the domain of integration is a square, 0, 1, 0, 1. The function that I'm integrating is dx1, dx2 over 1 minus x1, x2 over the square 0, 1 square. Well, this time, the domain of integration, well, again, you have a boundary, but we know about what to do about this one. Now, the only exceptional point is I mean, inside the domain of integration on its boundary, is a point x1 is x2 is 1. Before we had two singular points, there and there. Now we have just one singular point. What did happen? The following thing. Take the triangle and draw a small circle. There is a dangerous point here. Draw a small circle. And therefore it's a square. What we do is that we remove an infinitely small circle around the point. In algebraic geometry, it means blowing up. Exactly, blowing up. So what we have as a procedure of blowing up, you can blow in the plane, you can blow up this point. And then part of the difficulty disappears. Now you transform the integral, and the integral now is regular except at this point. Except at this point. Well, repeat. Do a blowing up. Do a blowing up. And that means now you have a pentagon. And believe me, a way to blow up is to introduce a third coordinate, which will be this one. Will be this one. So you get from a plane domain, a plane minus some line, to a three-dimensional surface in the three-dimensional space. You introduce a third coordinate. And the point is that when you do that, and the point is that the third coordinate is completely, if you look at the domain of integration, at this point, totally indeterminate. It's 0 over 0, 0 over 0, which means that in the three space, here you have a line. You have a line, vertical line. And then your square will be deformed. So there, well, we will not draw the picture. But then you have a fifth side, which is this vertical line. Well, perpendicular to the blackboard line. And then fourth, there are now 5 domains. And now the point is that when you go to this surface, the function that, the differential form that you integrate is regular at every point of the domain of integration, including the boundary. Including the boundary. So, now we are in a good position. We have transformed our space by blowing up. So now we have a surface in a three-dimensional space. On this, we have a certain domain of integration. We have a certain domain of integration. We know exactly where the boundary is. The boundary is in some union of some divisor. The boundary now is a union of 5 lines. On this surface, you have 5 curves corresponding to the 5 sides of this pentagon. And then, so you have an algebraic surface, you have 5 algebraic curves on this, and you have a domain whose boundary, a domain of integration, boundaries along these 5 curves. So if you work with relative cohomology, you can ignore, you can either remove this 5 line or work in relative cohomology, which is the same. Okay. And then now what you have, what you integrate is, when you integrate, is regular everywhere. And I show you the picture why it is so. Okay. Draw a very small circle around the dangerous point. When I replace the point by a small circle, it's a blowing up in the real geometry. In the complex geometry, you have to identify 2 points which are symmetrical on the circle, replacing the circle or the sphere by a projective space. Okay. Now, what you have? And this, the domain of integration is visible there. Domain of integration is visible there, of course. Now, where does the denominator vanish? This hyperbola. Look. No more eating. The dangerous curve, it's a small circle there and there, which are identified by symmetry. But the border of the domain of integration is out of that. And all the work is to generalize this to higher dimension, which is quite tricky geometry. I admit, quite tricky geometry. So now you see that I'm integrating a certain differential form with rational coefficient and so on a certain domain in an algebraic surface, on a domain which is a cycle modulo some algebraic variety. We are exactly in this general framework of integrating omega over domain D. Now we promote this to the motivic. That means we interpret now this integral not as an ordinary number, but you put an m, which is it means that you interpret it as a function on some algebraic variety acted by some group, and you have a specialization. So you have a certain function on an algebraic variety whose value at a specific point is this one. That's the end for the moment. Thank you very much.
Is there any question?
I suppose everyone is tired, including me.
Yeah.